Welcome to this comprehensive scientific lecture on the resources first inventive technique, a revolutionary approach to innovation and problem solving. The core principle is simple yet powerful, turning trash into tools by identifying and utilizing resources that already exist in a system but are currently going to waste. Let's start with the fundamental question that drives this entire technique. What unused resources already exist in this system? This single question can unlock tremendous innovation potential. Common unused resources include waste heat from machinery, unused volume in containers, mechanical vibrations, and idle processing time. These resources already exist in our systems, but serve no current function, representing lost opportunities. Let's examine waste heat, one of the most abundant unused resources in industrial and consumer systems. Fourier's law describes heat transfer, where Q is heat flux, K is thermal conductivity, and nabla T is the temperature gradient. Power available from heat transfer equals thermal conductivity times area times temperature difference divided by distance. Consider a typical industrial motor with a hot surface at 80 degrees Celsius and ambient temperature at 20 degrees, creating a 60-degree gradient. A typical computer processor dissipates 65 watts of heat that could potentially be harvested. With thermoelectric generators at 5% efficiency, we can harvest about 3.25 watts from processor waste heat. What resources are we currently throwing away? In data centers, millions of watts of heat energy are simply vented to the atmosphere. A single megawatt data center wastes 8.76 gigawatt hours annually, equivalent to powering 800 homes for a year. Mechanical vibrations represent another significant source of harvestable energy in our environment. The energy stored in a vibrating system equals 1/2 times the spring constant times amplitude squared. Average power from vibration harvesting equals 1/2 times mass times angular frequency cubed times amplitude squared divided by quality factor. A vibrating mass on a spring can be modeled as a harmonic oscillator, with energy oscillating between kinetic and potential forms. Consider bridge vibrations at 50 Hz frequency with 0.5 millimeter amplitude from traffic. A 100-gram harvester on this bridge could generate 0.77 milliwatts, enough to power wireless sensors. Piezoelectric floor tiles in train stations harvest footstep vibrations, generating up to 5 watts per step. With 10,000 steps daily, a busy tile generates 25 kilojoules, powering LED lighting for the area. Chemical gradients represent stored potential energy that can drive useful processes. Fick's first law describes diffusion, where J is flux, D is diffusion coefficient, and dC over dx is concentration gradient. The Gibbs free energy available from a concentration gradient equals RT times the natural log of the concentration ratio. Molecules naturally flow from high concentration to low concentration regions, and this flow can do useful work. Where rivers meet oceans, salinity gradients contain enormous energy potential. A river flowing at 1,000 cubic meters per second into the ocean carries 2.3 megawatts of osmotic power. What resources are we currently throwing away? Global rivers discharge enough salinity gradient energy to power 2 terawatts. Pressure drops in fluid systems represent wasted energy that can be recovered. The Hagen-Poiseuille equation shows pressure drop equals 8 times viscosity times length times flow rate divided by pi times radius to the 4th power. Power loss in a flow system equals volumetric flow rate times pressure drop. Fluid flowing through a channel experiences pressure drop due to viscous friction, dissipating energy as heat. Consider an industrial pipeline flowing at 100 liters per second with a 2 bars pressure drop. This system wastes 20 kilowatts continuously, which could be recovered with turbine generators. In microfluidics, we can redesign channels to use pressure drops for passive mixing instead of wasting energy. Idle time represents an often overlooked resource in computational and manufacturing systems. Most systems alternate between active and idle states, with idle time representing unused processing capacity. System utilization equals active time divided by total time times 100%. A typical manufacturing line operates at 65% utilization, leaving 35% idle time. This represents 3,066 hours per year of unused capacity, equivalent to 128 full production days. By scheduling maintenance, testing, and secondary production during idle periods, we eliminate waste. Wearable devices demonstrate practical applications of multiple resource harvesting techniques. Wearable devices can harvest body heat through thermoelectrics and motion through piezoelectrics simultaneously. Human body temperature of 37 degrees minus ambient 22 degrees gives a 15 degrees Celsius gradient. A 5 square centimeter thermoelectric generator on skin produces 0.15 watts from body heat. Human walking generates motion at 2 Hz frequency with roughly 5 centimeter vertical displacement. A piezoelectric harvester from walking motion generates an additional 0.05 watts. Combined harvesting provides 200 milliwatts continuously, enough to power smartwatches and fitness trackers indefinitely. Industrial processes generate numerous waste streams that can become valuable inputs for other processes. Industrial ecology uses waste cascades, where the waste output of one process becomes the input for another. A chemical plant producing 50 tons per day of CO2 waste can feed algae bioreactors. Algae can convert 60% of that CO2 mass into biomass, yielding 30 tons of algae daily. Converting 30% of algae biomass to biodiesel yields 333 gigajoules per day of fuel energy. What resources are we currently throwing away? Industrial CO2 emissions represent 37 billion tons annually of potential chemical feedstock. Unused volume in structures and containers represents three-dimensional resources for additional functionality. Hollow structural elements contain significant empty volume that could house sensors, batteries, or thermal storage. Available volume equals total volume minus the volume occupied by structural material. Modern aircraft wings contain roughly 40% void space between structural ribs. A large aircraft wing with 150 cubic meters total volume contains 60 cubic meters of usable space. This space enables integrated fuel tanks, distributed avionics, and heat exchangers without adding external volume. Even electromagnetic interference, typically considered noise, can be harvested as a power source. Power available from electromagnetic fields equals electric field squared divided by resistance. Rectifying antennas convert ambient radio frequency radiation directly into DC electrical power. Dense urban environments contain roughly 0.1 microwatts per square centimeter of harvestable RF energy. A 100 square centimeter antenna array harvests 10 microwatts, sufficient for ultra-low power sensors. Near cellular base stations, power density increases 100-fold, enabling milliwatt-level harvesting. Agricultural operations generate enormous biomass waste that represents concentrated chemical energy. Energy content of biomass equals mass times heat of combustion. Anaerobic digesters convert agricultural waste into methane gas, closing the carbon loop. Corn harvesting leaves approximately 5 tons of stover residue per hectare in fields. At 15 megajoules per kilogram, this represents 75 gigajoules of energy per hectare. A 1,000-hectare farm could generate continuous 2.4 megawatt power from crop residues. What resources are we currently throwing away? Globally, we leave 5 billion tons of crop residue to decompose uselessly each year. Sound waves carry mechanical energy that can be converted to electricity in noisy environments. Acoustic intensity equals pressure amplitude squared divided by twice the density times sound speed. Available acoustic power equals intensity times collection area. Acoustic harvesters use resonant structures to convert sound pressure oscillations into electrical current. Heavy industrial environments commonly reach 100 decibel sound pressure levels. 100 decibels corresponds to an acoustic intensity of 0.01 watts per square meter. A 10 square centimeter harvester at 30% efficiency captures 30 microwatts from this acoustic field. These harvesters enable self-powered sensors for continuous noise monitoring in factories. Gravitational potential energy from height differences represents a fundamental unused resource. Gravitational potential energy equals mass times gravitational acceleration times height. Hydroelectric power equals density times gravity times flow rate times head height. Water falling through a height difference releases potential energy that turbines convert to electricity. A tall building with water storage at 50 meters height stores significant gravitational potential. Flow of 1 liter per second through 50-meter height drop yields 490 watts of recoverable power. Installing microturbines in building downpipes recovers energy from water distribution systems. Phase change materials store and release large amounts of thermal energy at constant temperature. Heat stored during phase change equals mass times latent heat of fusion. Phase change materials absorb heat during melting without temperature rise, storing thermal energy efficiently. Common paraffin wax stores 200 kilojoules per kilogram during its solid-liquid phase transition. A 100 kilogram thermal battery using paraffin stores 20 megajoules of thermal energy. PCM systems capture daytime waste heat and release it for nighttime heating, matching supply with demand. Modern PCM thermal storage systems achieve 85% round-trip efficiency. The true power emerges when multiple resource streams are integrated into cohesive systems. System integration of multiple resource harvesting techniques amplifies overall efficiency and resource utilization.